Hey guys, today's video is on intermolecular forces, arguably one of the more important concepts that we'll talk about this year. So when we talk about molecules, of a liquid or a solid, we know that these things are composed of atoms held together by intramolecular forces. And we refer to these things as bonds, right? Either covalent or ionic. And again, these are within a single molecule or perhaps crystal lattice in the case of ionic compounds. But individual molecules are aggregated together in a large sample by attractive forces called intermolecular forces, and these exist between molecules. So when we talk about this aggregation, we mean that these molecules can actually clump together, okay? We first saw this year when we talked about gases, right? And when it comes to ideal gases, we can largely ignore this clumping. We can largely ignore these attractive forces in between molecules, okay? That being said, we know that these intermolecular forces are substantially weaker than bonds. And I'm going to reiterate this a couple times today, okay? For example, when we give heat, supply heat to a sample of water, okay? We can transition that water from the liquid to the gaseous state so that heat or kinetic energy is sufficient to overcome the intermolecular force of attraction between the partial positive hydrogen of one water molecule and the partial negative oxygen of a separate water molecule, right? This can be kind of cleaved or can be kind of overcome with sufficient kinetic energy. That being said, what does not happen is this intramolecular bond. We don't actually break an oxygen-hydrogen bond within a single molecule, okay? We just have the ability to separate them out. And in doing so, because we increase the spatial arrangement, we can transition from the liquid to the gaseous state, okay? Now, today's video is going to focus on two types of intermolecular forces, and they should seem familiar from honors chemistry. That being said, we're going to go into kind of a deeper dive. The two kind of overarching categories is going to be our dipole-dipole that exists only between polar molecules, and also London dispersion forces, which exist for every type of molecule. However, nonpolar molecules and noble gas atoms, this is the only force that they actually experience. So again, we're talking about things like, say, helium, neon, argon, krypton, so on and so forth, okay? All right, let's kick things off with dipole-dipole. When we talk about dipole-dipole, we're talking about an intermolecular force between molecules that possess a permanent dipole, right? So we need a molecule that has a permanent dipole. We need a second molecule that also has a permanent dipole. This necessitates that these molecules are polar. The origin of the source of attraction is the electrostatic or the electromagnetic force, as kind of described by Coulomb's law. That being said, per Coulomb's law, when we talk about charge, or in this case, the extent of the dipole, how polar that bond is, this will dictate the force of attraction, with a larger dipole yielding a greater force of attraction. So here I've indicated the familiar hydrogen monochloride molecule, or the hydrochloric acid, if we dissolved it in water. Clearly the chlorine is more electronegative, and as such we have a dipole that's pointing towards that more electronegative atom, right? So electrons are migrating towards the chlorine. What I've done here is I've oriented 4 different HCl molecules such that we see that between the partial positive hydrogen of one molecule and the partial negative chlorine of a separate molecule, this right here is your dip-dip. This is your dipole-dipole intermolecular force, okay? And we see that the way these molecules have oriented themselves in space, we see another dipole-dipole force of attraction here, 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 and here. Okay, so again, we have this kind of optimization of alignment. We're looking to maximize these attractive forces. And this arrangement will go on in all directions, right? Not just a snapshot of 4 molecules, but some insanely large number of molecules, and also in the 3 dimension, okay? So besides the familiar dipole-dipole, we can also discuss what's called ion-dipole forces. So instead of having 2 molecules that are both polar, in this case, we're just going to have one molecule that's polar, and that's going to interact with an ion. okay? Again, Coulomb's law can be used to explain this, where we have, again, an attraction of an ion with a polar molecule. The strength of this intermolecular attractive force is dependent on two different things. It's dependent on the charge and the size of the ion in play, right? So that first kind of component here. It also depends on the magnitude of the dipole moment of the polar molecule in addition to that size of that polar molecule. So two things that we're looking to consider here, okay? When we talk about the size of an ion, normally the intermolecular force for an ion dipole is going to be larger with a cation, simply because cations are usually smaller than their anion. If we're talking about, say, like some isoelectronic series, and because it's smaller, that charge is going to be a little bit more concentrated. So let's take a look at an example of sodium ion, this cation, interacting with water. Given the size of sodium and the fact that it's a +1 charge, we find that this IMF, intermolecular force, is rather weak. Given the fact that magnesium ion is twice the charge of sodium and it's a smaller atom, this ultimately yields a rather strong ion-dipole force. Again, relating back to Coulomb's law, force equals K Q1 Q2 over D squared. You know, whenever we can make this smaller, that's going to drive down the distance. And whenever we can have a larger charge, say +2 as compared to +1, that's going to bring up this term. Both of these things reinforce each other to ultimately arrive at a stronger intermolecular force, okay? Pushing on, we're gonna visit kind of a really strong, kind of special case of this dipole-dipole. And this is our familiar hydrogen bonding. Okay, so again, this is a special type of dipole-dipole where a polar molecule, so it has to be a polar molecule, is going to have a hydrogen directly bonded to an oxygen, nitrogen, or fluorine. Okay, the reason this is special is because it is stronger than a traditional dipole-dipole interaction. Okay, the reason for this is because the hydrogen atom is so small, okay, that it allows for neighboring molecules to be really, really close in proximity, right? These dipoles can be really close. And also because the electronegativity difference between the hydrogen and any of these three atoms is so great that this bond is going to be highly polarized. Let's take a look in the context of HF, okay? So here we find that between the fluorine and the hydrogen, we have an electronegativity difference of 1.8. This means that the electrons are largely migrating towards the fluorine. And it's so electronegative that essentially what this fluorine does is it strips the hydrogen atom of its single electron. And so we essentially leave behind just a proton. So this isn't just a polar bond. This is like almost bordering on ionic, right? It's almost bordering on electron transfer, a full electron transfer, okay? That's how greatly polarized this bond is. So it's not that this is like partial positive and partial negative. It's that this is insanely partial positive and insanely partially negative, almost bordering on full-on charges, okay? If we consider another kind of classic case of hydrogen bonding, let's evaluate our kind of water molecule here. What we find is that a single water molecule has the capacity to hydrogen bond up to 4 other water molecules, maximizing the partial negative of the oxygen of one water molecule, with the partial positive of a hydrogen of a neighboring molecule, again, maximizing those attractive interactions, okay? Again, we have a really, really polarized bond. We have this really large charge separation. And as a result of being able to bond 4 separate water molecules, this gives rise to a lot of the unique properties that exhibit or are exhibited by water, okay? Just as kind of a really important point here, though the term would suggest that it is a bond, it is not. Again, hydrogen bonding is an intermolecular force. It is not an intramolecular bond, right? This dashed line is suggesting an interaction, where this solid line is suggesting a formal bond, a sharing of an electron pair between separate atoms, okay? Just to kind of really drive at this difference in strength between hydrogen bonding and dipole-dipole, let's just take a look at an example where we evaluate the melting points and boiling points of a hydrogen bonding kind of capable molecule with just a normal polar molecule. Its only intermolecular force is that of dipole-dipole. So a water molecule has a melting point and boiling point of 0 and 100 respectively. This should be in degrees Celsius. While our H2S here only has a melting point of -82 and a boiling point of -60, okay? Now again, water has the capacity for hydrogen bonding. Our H2S molecules, those are polar, sure, but they're held together only by regular dipole-dipole. The idea being is that these hydrogen bonds, tie up these water molecules so well that you need a fair amount of kinetic energy first to melt and then ultimately to boil relative to our H2S here, okay, where you don't need as much kinetic energy to transition from the solid to the liquid state and then from the liquid to the gaseous state. Okay, so already you should be equating strength of intermolecular forces with things like melting points and boiling points. We push on, and we are going to talk about kind of our second category here, that of dispersion or London dispersion forces. Largely we'll abbreviate these as LDFs, okay? In nonpolar molecules, or again, noble gas atoms, these are the only intermolecular force that exist, okay? It's like dipole-dipole, but rather than being permanent because we have some polar bond, these are instantaneous, they are fleeting, and they require kind of a polarization. And we'll get into this as far as like size and shape goes, okay? Bottom line is these can occur randomly, and as quickly as they occur, they can also kind of dissipate, okay? So let's take a look at diatomic molecular hydrogen. We have 2 electrons here, and because it's the same atom and it's the exact same electronegativity for both hydrogen atoms, we're going to find that there is a symmetric distribution of electrons, right? That these are spread out equally. That being said, electrons are constantly in motion, right? So it could happen that by chance, as these electrons kind of jiggle, they could tend towards one side, where again, by chance, both electrons have kind of migrated towards one area of the molecule. And as a result, we have this polarization that takes place, okay? Where now we have this, asymmetry as far as electron distribution goes. As this happens within one hydrogen molecule, we find that it has the capacity then to induce a dipole in a neighboring hydrogen molecule. So this is the molecule we just took a look at. As it comes into contact with a neighboring hydrogen molecule, this electron richness of the one H2 molecule has this ability to, per electrostatic repulsion, drive the electrons in this molecule to the opposite end, right? So it induces a polarity in this neighboring molecule. And it's this attractive force between the weakly partially negative of one molecule and the weakly partial positive of a neighboring molecule that we identify as the London dispersion force, okay? Now, when we talk about these London dispersion forces, there's a number of things we've not yet considered. If we go back to, say, chemistry or your sophomore year, we'll say that these dispersion forces increase in 2 different ways. 1, with increasing contact area between molecules, and 2, with an increased polarizability of the molecules. And there are 4 things I've identified here that increase the polarizability of a molecule. First off, the more electrons there are, the larger kind of separation that can occur. We refer to this as polarizability. The bigger the electron cloud is, okay, more polarizable. If we have electrons that are not kind of tightly held in place, such as like a sigma bond, but rather these are a bit more delocalized and have this propensity to kind of move about, more polarizable. Bigger atoms in general. So as we work down the periodic table, because these outer electrons are held less tightly by their nuclei, they have this ability to kind of migrate a little bit. And as they migrate, again, we describe these atoms as more polarizable. So just to kind of recap here, I would define polarizability as the ability to have large charge separation. Okay? So just to kind of firm this up, let's say we're taking a look at bromine versus hydrogen. Again, bromine, really, really large atom. It has a really, really large electron cloud, okay, relative to, say, hydrogen. So what we find is because we have 70 electrons in this molecule just kind of floating around, when we have this asymmetry, right, when we have these electrons kind of jiggle to one side of the molecule and kind of leave behind this deficiency, we can get this really large charge separation where it's not that, again, this is partial positive and partial negative, but it is extremely partial positive, extremely partial negative, really, really great charge separation. And so the strength of this London dispersion force is really, really significant as compared to this London dispersion force between two hydrogen molecules. And we can verify this through looking at the respective boiling points, where we find that the boiling point, which again is kind of a measure of the strength of this London dispersion force, is really high for bromine as compared to quite low for hydrogen that has this propensity to stay in the gaseous state. Okay? So we've just evaluated essentially this idea of increased polarizability. The other thing we need to consider when it comes to dispersion forces is this idea of contact area. So let's say we're going to evaluate two isomers of C5H12. Okay, we're going to look at just the normal straight chain pentane or N-pentane versus the isomer, the structural isomer 2,2-dimethylpropane, and here are those respective structures. Again, if we can essentially increase the contact area between molecules, this means that we have a greater chance for these dispersion forces to actually kind of take hold. So what I've done is I've drawn kind of an electron cloud around the normal straight chain pentane, two molecules kind of together here, versus the 2,2-dimethylpentane. I'm sorry, 2,2-dimethylpropane. And what we find is just there's an increased contact area between these two molecules as opposed to these two molecules, right? Because the structure is more compact, there's less opportunity for contact. As a result, we have fewer dispersion forces. This should lead to a weaker attractive force between those two 2,2-dimethylpropane molecules, okay? As a result, they're close, but the boiling point for pentane is larger than the 2,2-dimethylpropane because these forces are weaker. It takes less kinetic energy to take these two molecules and essentially separate them and transition from, that liquid to the gaseous state, okay? That being said, I think students very often attribute dispersion forces with being incredibly weak, and that's true. However, in all circumstances, we always need to evaluate data, right? We can make assumptions, but data rules, okay? So in many cases, dispersion forces are comparable to or even greater than dipole-dipole forces, okay, that exist in polar molecules, okay? So let's say we were to compare tetrachloromethane, okay, so CCl4 versus fluoromethane. Nonpolar molecule, so strictly dispersion forces, yet, pretty high boiling point, right? Versus this polar molecule, which we attribute with having these stronger dipole-dipole IMFs, also dispersion forces, actually has a pretty low boiling point. Okay, so what we find is that in the absence of data, maybe we would identify this as having weaker intermolecular forces, but with data, we actually can verify that these dispersion forces, because we have a very polarizable molecule with all these lone pairs, with all these electrons of these 4 chlorine atoms, right? We have so many more electrons in this molecule than we do here. It's that polarizability that's going to increase the strength of the dispersion forces, so much so that they actually outweigh the strength of this dipole-dipole force, and that manifests in a larger boiling point. Okay. Another point about intermolecular forces is that we often see these, in the context of biomolecules. So, in very large biomolecules, these non-covalent interactions, again, these IMFs, may occur between different molecules, which is what we've seen here, or because these molecules are so large, they can actually occur in between regions of the exact same really large biomolecule, okay? I think a really good example of that is in proteins. So let's say we are talking about amino acids, right? Making up some polypeptide. And we know that the side chains of all these amino acids are going to be a little different, okay? Hydrogen bonding that occurs in the peptide backbone between these different amino acids, right? So if we have like some, polypeptide chain, and this is representing some R group, and this is representing another R group, it could be that hydrogen bonding, exists in between these R groups within the exact same polypeptide chain, within the exact same molecule, right? And it's these hydrogen bonding, depending on the spatial arrangement and exactly kind of how far apart they are within the polypeptide backbone, that can dictate things like secondary structure, right? We can get these beta-pleated sheets. We can get alpha helices that form because of these hydrogen bonds. That being said, when it comes to, say, the quaternary structure of a protein, if we already have these existing polypeptide chains, and maybe this one is already kind of like folded in some way, and this one is already folded in some other way, it could be that we have these hydrophobic regions, right? These areas where all the side chains are nonpolar. And as a result, we find that they can kind of lock into place in some specific conformation. So again, we can have these intermolecular forces that exist not just within the same molecule, but between neighboring molecules that bring together now not just like these separate amino acid chains or these separate proteins, but can make some really large complex, resulting in a quaternary structure. So as far as these dispersion forces, we find there are other ways to induce dipoles besides just a nonpolar molecule and another nonpolar molecule. It turns out that when we have an ion or a polar molecule placed in proximity near an atom or a nonpolar molecule, the electron distribution of said atom or molecule can be distorted a little bit by the force that's kind of being exerted by the ion or polar molecule. So let's take a look. Let's say we have this nonpolar molecule or an atom. And right now I have no partial charges because we have a symmetric or even distribution of electrons. But let's say we bring in close proximity a cation, for instance. Well, now these electrons within this nonpolar molecule are going to tend towards the left side of this molecule because they're going to be attracted by the positive charge of the cation. So this cation, in effect, induces a dipole. Okay? We find the same thing can occur if we bring a nonpolar molecule in close proximity with a polar molecule, where we have this established dipole. So I've tried to indicate the difference between the polar molecule and our familiar, formerly nonpolar molecule. As soon as we bring this molecule, this polar molecule with a permanent dipole in close proximity with a molecule that formerly had this symmetric or even distribution of electrons, these this partial negative charge can literally push the electrons in this molecule away. And now we have a induced dipole, right? And I've failed to draw in the attractive force between the ion, and again, formerly nonpolar molecule, and this polar molecule that has an existing dipole, and again, the formerly nonpolar molecule. But so again, we can have an induction that takes place not just between two nonpolar molecules, as in the case of a true dispersion force, but ions and polar molecules can induce dipoles within formerly nonpolar molecules. The strength of these induced dipoles relies on two major things. When we talk about what is inducing, right, we care about the charge of the ion, +1, +2, -1, -2, and also the dipole, that's maybe existing within the polar molecule. So either of these, ions or polar molecules, have the ability to induce a dipole. Besides that, when we talk about what is being induced, we really care about the polarizability of that nonpolar molecule. How easy is it to create a really large charge separation? And this is really easy, again, for atoms that are really large, have a lot of electrons, have really large atoms that don't really hold on to their electrons all that well, okay? Whew, it's been a lot so far. just a quick summary, and this will look really familiar from last year. So bottom line, we kind of have these, maybe 2, maybe 3 overarching categories. As far as relative strength goes, hydrogen bonding is going to be traditionally stronger than dipole-dipole, and that will traditionally be stronger than dispersion forces. Okay, recall that dispersion forces, every single molecule has these. Polar, non-polar, doesn't matter, you got dispersion forces. Okay, that being said, non-polar molecules only have these. When it comes to dipole-dipole, you got to be polar, right? We have to have this permanent dipole that exists, and it comes into contact with another polar molecule where there's a permanent dipole that exists. And if we are a polar molecule, and we specifically have a hydrogen directly bonded to a fluorine, oxygen, or nitrogen, we have this kind of third case here, just a really strong special case of dipole-dipole. So, if you have hydrogen bonding, you have all 3 types of IMFs. If you have if you have dipole-dipole, you have dipole-dipole and dispersion. And if you're a nonpolar molecule and you just got dispersion, well, you just got dispersion, okay? So if you identified a molecule had the capacity to have hydrogen bonding as its IMFs, you would say it not only has hydrogen bonding, it has dipole-dipole and dispersion. You would list all 3. Okay, if it's polar and has dipole-dipole, you would say it has dipole-dipole and dispersion. Non-polar, just dispersion. Okay, but again, this rank ordered list is good, but it is predictive. Okay, you got to look at data. If ever you're given data, that's what we would use in order to discuss the relative strength of IMFs in molecules. Okay, we'd look at things like boiling point, melting point, vapor pressure, which we'll get to, density, solubility, surface tension, viscosity, the list goes on and on. Okay, so we can use these different properties, which are dictated by IMFs, to kind of go back and rank order molecules if given the appropriate data. Okay, we spent a lot of time talking about these IMFs. I think it's worth noting that as strong or weak as these things are, even if they're strong, even if you have these enormous dispersion forces or really strong hydrogen bonding, it is still so substantially weaker than an intramolecular force, right? An intramolecular bond, such as covalent or ionic. Thanks, guys.